the EAGE Technical Community on Wind Energy, we would like to welcome you on this talk on the floating turbines by Jordan Geear. We're gonna have a proper introduction to Jordan later on. So the agenda for tonight is first we give you a short, very brief introduction to the EAGE Technical Community on Wind Energy. Then we're gonna have to going to the highlight of today, obviously the presentation of Jordan, followed by some questions. And again, for those joining a bit later, you can ask questions in the chat, or you can also use your microphone and direct your questions to Jordan right after he's done with the presentation. And then we're gonna close up with it. Okay, so to the introduction of the EAGE Technical Community on Wind Energy. So basically, who are we? And so this sentence here is basically summarizing, we're a network of members interested in sharing the knowledge and developing the skills among geoscientists and engineers supporting offshore wind energy. At the moment, I think we're rather on the geoscience side when it comes to the committee members, but we really much welcome also all the engineers, because this the efforts that we're doing in offshore wind with the subsurface characterization is really properly integrated one. And yeah, really, it's not only a geoscience group, it's also, we welcome engineers, modelers, basically anybody who has to do with what impacts the foundations and the setup for offshore wind in general. So we are established in 2024, a rather young community, 1 year old, so to say, but we already count more than 1,000 members. So here the count says 1,120 plus. So that's quite a big success for such a short time, but we are hoping to grow further in the near future. Next slide. So who are we in person when it comes to the committee? You see here all the committee representatives. We cover quite some good share of Europe at the moment, but we're not limited to Europe. So if you're very much interested in being part of this committee, just let us know via EAGE, or you can also, if you know one of us, just forward an email and we will discuss that. We're really open. Also, the committee can grow further, and we will definitely consider your application. So that please let us know if you're interested in joining our committee in the future. And the activities. So we participate at the EAGE Annual, GET Conference, and other events. EAGE Annual, the next one will be, I think it's in June 26 in Aberdeen. GET Conference very soon, in 2 weeks' time in Rotterdam. And we have also some other events where we are helping contribute to. Then the second point, we're educational networking events and collaborations such as this one. And we also hope to increase a bit. We have a LinkedIn page to bring out some news, career advice, and also promote vacancies, jobs. So that's mainly done via the LinkedIn channel that we are doing. Next slide. So yeah, if in case you're interested, please scan this the picture here. Really, we want to hear from you. We want to share our expertise, but also yours. Join the conversation, and all together, we really hope to make a better network and to shape the future of offshore wind in the best way. Yeah, again, we're very much open to any new committee members, but also as this event, we hope to be. This is the first basically webinar of this community, and we hope to make it monthly or bi-monthly thing. So in case you have any suggestions on potential speakers for the future, also let us know. We're very much interested in getting to know what your opinion is on potential speakers and topics for the future. Next slide. Good. As mentioned, in a very short time, we're gonna have this GET conference, and there is like GET is 4 renewable energy conferences in one, and the blue one there to the right, that's the Offshore Wind Energy Conference, where yeah, it's 4 days, or 3 days with some pre and post conference workshops where you can learn a lot about offshore wind energy. So the program looks quite promising. Check on the webpage of EAGE or the Get page directly, and yeah, I would very much highly motivate you to join this conference because yeah, it's really a different variety, a big variety of topics that we cover, and there is a lot to learn for I guess for anybody. Also, if you have been working on offshore wind for quite a bit already. So Get 2025. Then the next slide is a bit if you're planning. You cannot plan this anymore because it's going to be in Australia, and unless we have some people listening from Australia here in the group, it's probably too late because you cannot join remotely. But this highlights a bit. There is this third EAGE SUT workshop on integrated site characterization for offshore renewable energy. We had one before, I think, in Boston and in the UK, Newcastle, I think it was. And this is also highlighting how EAGE collaborates with other associations such as the SUT. And yeah, that's the first 2 workshops were a big success, and I guess we will make similar conclusions after the Melbourne event. But of course, from Europe, I think there will not be so many people participating. But it's really great to cover all of the globe and all of the offshore wind activities in this framework here. Good. Next slide. Yeah, thanks for joining the webinar. And then I think we go to Jordan, because the topic, yeah, we're going to focus on floating turbines, grounded investigations, so the flexible survey approaches for floating wind. And it's Jordan Geear from Global Maritime that is speaking. And with that, I think we give the word to you, Jordan, and then you can also introduce yourself as you know yourself the best. So, looking forward to your presentation and then the Q&A afterwards.
Great, thanks, Benjamin, and thank you all for attending this webinar today. My name is Jordan Geear, and I'm a Global Business Lead for Engineering Geology at Global Maritime. My background is primarily in offshore ground modelling for renewable energy sites and in the planning and execution of geotechnical site investigations for those sites, with a particular focus on floating offshore wind. And I've been in the industry for around 10 years in a site characterization related role. Just going to share the presentation. Hopefully everyone can see that. So,
yes.
Thanks. So the focus of my presentation today is on planning and execution of flexible ground investigations for floating offshore wind projects. I'm going to start with an introduction to the general challenges associated with how we characterize the ground for floating offshore wind farm sites specifically, and how this differs from fixed wind renewable sites and oil and gas sites. And then the main focus of the presentation will be in introducing work completed by Global Maritime on behalf of Offshore Renewable Energy Catapult and the Floating Offshore Wind Centre of Excellence. This is the MA17 project, which has looked at planning and execution of site investigations for floating offshore wind projects and developing site investigation strategies for those projects. So just to provide some context for anyone not familiar with floating wind industry, floating wind can be executed or is being planned to be executed as a number of different substructure and anchor concepts. And this has a significant series of implications on how we plan and execute ground investigations and ground modelling for floating offshore wind in terms of meeting the requirements. So you can see that floating wind turbines may have a range of different substructure concepts, ranging from semi-submersible type concepts with spread mooring systems, which can take form of catenary, semi-taut, or taut mooring concepts. These typically have a wide mooring radius and can be used with, depending on the specific concept, horizontally or vertically loaded anchor concepts. This then ranges through to concepts such as the tension leg platform, which utilizes anchors that are vertically loaded, and this has a much tighter mooring radius, with the anchors being the tighter cluster below the substructure associated with the turbine. And then these substructure concepts can be used in conjunction with a series of different anchor types, ranging from drag and bedded anchors. So you think of concepts similar to a typical ship anchor, through to driven piled, gravity installed, vertically loaded anchors, and Jordan grouted anchors, as well as suction anchors. This illustrates, I think, immediately that there's a significant potential optionality in concept floating with floating wind, and this is going to be a theme of the presentation going forward. So what are the specific challenges for characterization of the ground for floating wind? Potentially, there's much greater heterogeneity in the ground conditions over a mooring footprint than there would be over, say, a typical jacket footprint for fixed wind. There's also a significant increase in the numbers of individual foundations or anchors, say relative to piles for fixed wind, and these are much further apart than they would be in terms of the equivalent fixed wind. As mentioned, there's significant optionality seen in mooring configuration, mooring radius, anchor type, and that is only potentially going to be defined well into feed or detailed design, so late project stages, and therefore specific infrastructure locations will not necessarily be fixed until later on in the project, at which point it becomes more program critical to plan the GI and execute it efficiently. There's also potentially more limited positional certainty with specific anchor concepts. So anchor concepts such as drag and bedded anchors, DEA, have a drag path over which the anchor is installed, and there's a need to characterize large volumes of ground to fully characterize, for instance, these drag paths, or volumes of ground for anchors that have a lower positional certainty during installation. There's also a challenge around existing best practice in the industry and how this relates to scaling of projects. So most of the existing best practice for geotechnical site investigation for floating offshore wind is conceived from existing oil and gas experience. There is developing best practice certification body recommended practices that are looking at this as part of industry projects. However, the current written recommended practices typically advocate an anchor-specific approach. So the number of exploratory holes or holes of CFTs that are conducted to characterize the ground, the anchor locations, are dependent on soil variability across the anchor pattern, according to the current standards. But these recommended practices, I should say, typically would advocate either one borehole or one co-penetration test per anchor in areas of high potential geological variability, and potentially if we can make a determination that the anchor cluster, i.e. a pair of anchors or multiple anchors within a cluster, are in an area of lower geological variability, to adopt a one borehole or one in situ test per cluster, with support from the ground model, which characterizes the ground conditions over that cluster and makes a determination that the cluster shows limited geological variability over that body of ground. Potentially sort of following this guidance for floating wind and scaling this up may lead to large numbers of individual points. So if we take the extreme approach of one exploratory hole per anchor, for a 3 gigawatt site, there may be over 1,000 individual exploratory holes. That's quite an extreme example, but even for a 1 gigawatt site, we're looking at sort of around 300 holes, and this potentially creates supply chain constraints for development of these projects. It limits the work that could be undertaken with the specific weather windows that are favourable to offshore investigation. So it's important that we look at potentially rationalising this and potentially looking at more targeted methods of investigation. Touched upon heterogeneity in the ground conditions. So for floating wind, as I said, there's a large number of individual anchor points, individual substructures, if you like, versus fixed wind. So within say a typical jacking substructure would be interested in ground variability over say a 30 metre by 30 metre area, or up to 50 metres if we're looking at micrositing the structure. Within a spread mooring footprint, we're interested in a 1 kilometre radius, which would have potentially 6 anchors within that radius. So we need to understand in great detail how the ground conditions vary over this footprint, and certainly over a cluster of anchors. I mentioned again optionality. So what we're seeing with current floating wind projects is that significant optionality may exist in both the anchor layout and the inter-array cable layout until relatively late stages in the project, driven by the mooring layout and the analyses that inform this. Final layout may be defined late in the project, so during FEED or detailed design, limiting the time it's available to plan, procure, execute an anchor or cable route specific geotechnical survey. However, what we're seeing is to inform that routing, to inform that anchor selection, potentially quite detailed site-wide coverage of data is required to inform that early anchor design, routing, optioneering, and potentially if projects are using the PCI approach, we're looking at requiring detailed information early on to provide reliable information. So a lot of the potential solutions to this, so potentially kind of greater reliance on the use of geophysical survey and ground models to move away from large numbers of exploratory holes or in situ tests. This approach would involve generating a detailed site-wide ground model at a relatively early stage, but then extracting soil profiles at anchor locations using site-wide geophysical survey that's been calibrated at locations that are disparate to the anchor locations we're interested in. This may potentially be required to enable that optionality at a later stage and be resilient to changes in anchor location later on in the project. Potentially, we could also look at reducing our reliance on physical sampling, which has potentially long lead times associated with laboratory testing, and focusing more on in situ testing. And we also need to be cognizant of, while project program and cost is a factor, we need to satisfy ourselves that the selected site diversification approach accommodates the project program while be appropriate to the level of ground risk and the project's tolerable level of ground risk in particular. So that was an introduction to general challenges. I'm now going to move on to presenting a summary of the site investigation anchoring MA17 project that was delivered on behalf of Offshore Renewable Energy Capital, with the aim of investigating these challenges and developing potential solutions through a cost and risk assessment based approach to site investigation planning. Before I start on that, I'd like to say a few words about the Floating Offshore Wind Centre of Excellence that initiated the project. This is a collaborative program with between industry, stakeholder, academic and supply chain partners, which is aimed at accelerating floating wind projects, assisting with the commercialization of these projects, strategy around delivering net zero and driving economic growth. And this is achieved by developing a series of strategic programs in collaboration with through Renewable Energy Catapult and the organisations that are shown on the right-hand side of the screen there. This is looking at a number of different strategic programs such as mooring technology, substructures, dynamic cabling, environment, and supply chain. And the MA17 project is one, just forms part of one particular program initiated by the Centre of Excellence. Recent work that was undertaken by the Centre of Excellence highlighted the specific challenges that I've just discussed relating to availability of site investigation data for floating wind projects, and identified in particular site characterization as a challenge around mooring and anchoring, as well as dynamic cables. And this project therefore came about by to address in part the challenges that I just discussed. So the scope of the MA17 project was to undertake a detailed site investigation method assessment to look at what methods are available for characterizing anchor locations and cables, scrutinizing the efficiency and practicality of those techniques, and undertaking a SWOT analysis of strengths, weaknesses, opportunities, threats for those methods. I won't focus so much on that aspect of the project today. However, the other aspects of the project were to undertake a cost risk evaluation of different GI strategies, so assessing the balance between GI cost and the technical sufficiency of that to the project. Project also looked at clarifying logistics, so understanding what vessel types were available in the market, where the workability associated with the techniques, equipment costs associated with this, and project timelines. And this was in particular done both for standard GI techniques, but also for novel site investigation techniques. So Jordan was particularly interested in looking at how novel techniques could assist in addressing these challenges, and aim to clarify the understanding of those techniques and limitations. And as part of the same project, looked at a range of ground conditions associated with the UK continental shelf, and identified specific geohazards, geoconstraints that are relevant to those techniques and to SI plan for floating wind. So how did the project undertake this? So the approach adopted for the project was to develop a series of conceptual ground models and indicative anchor geometries for 5 hypothetical floating wind farm sites that represented different ranges of ground conditions across the UK continental shelf. And the aim was to bound the range of ground conditions and look at different potential levels of ground risk, different geohazards, to also look at sites that were representative of different anchor technologies, the site investigation requirements specific to those technologies. At that point, there was an exercise in looking at developing a series of strategies appropriate to each site, again covering different levels of risk, different program and cost levels. These range from anchor-specific GI through to approaches more reliant on the ground model and general site-wide characterization. The project also looked at minimum viable site investigation approaches and site investigation approaches specifically for CLP. These strategies were then modelled to understand duration, cost, weather workability of each strategy and each technique within that. These are also then risk assessed with respect to technical risk and program risk. And then this was then formulated into an overall cost program risk evaluation for each set of strategies. So I mentioned those different strategies. Broadly, the two main strategies, overarching strategies considered were, as I said, the ground model based approach, where, as you can see in that example, we developed a detailed ground model based on locations across the site. This then is potentially more resilient to changes in anchor location, but you can see from the left-hand image that those geotechnical survey locations are not necessarily positioned at anchor locations. This is reliant on geophysical survey coverage to provide indication of the soil profile at each anchor location, each anchor cluster. This is then the other end spectrum. You have anchor-specific or anchor cluster-specific approaches where anchor locations are defined and then intrusive GI is carried out at each anchor location. It's a more traditional approach that is conceived from oil and gas practice. Now, as an engineering geologist, I like to relate everything back to the outcrop. And another thing that we looked at and bore in mind when doing this project was assessing the variability. As I mentioned, those conceptual ground models for each site were designed to represent different levels of variability in ground conditions and sensitivity to different anchor concepts. So we looked at the range of conditions from those that we expected to represent a low degree of variability in soil type, strength, compressibility. Ground conditions where there was expected to be industry experience that would be available to assess potential variability, including from oil and gas experience, and sites where there was expected to be more predictability in geotechnical properties. At the other end of the spectrum, we have sites where there would be expected to be significant lateral variability in soil and mooring footprint, potentially active geohazard processes, and also low levels of experience previously in the industry with respect to anchoring techniques. I've just put in a few images to illustrate what that could look like in outcrop, and clearly this gives us a much better understanding of potential variability in the soil than in the ground than we would necessarily see in, say, a borehole or from geophysical surveying. So you can see this essentially you could range from what you've got on the left, so fairly homogeneous glacial marine or glacial lacustrine phase through to significant heterogeneity in terms of soil type, including subglacial soil deposits and active debris flow processes, for instance. And so we tried to bound these range of conditions with the sites we've considered. So for each of these 5 sites, we developed a conceptual ground model shown on the left, so we could understand variability across both the site and the anchor footprint from a conceptual standpoint. We assigned indicative ranges of properties to that to enable anchors to be sized on a hypothetical basis to inform the study. We also developed a 3D voxel model for each site to enable that variability to be visualized as well. And these conceptual models have both value in understanding the ground conditions for the study, but also I think they have a wider value in providing a resource to understand geoconstraints on the UK continental shelf. In addition to development of the ground models, each site was assigned a hypothetical layout for a floating wind farm site, and this was based around a 1 gigawatt floating offshore wind farm site. This was developed both for semi-sub and for TLP substructures over a range of metocean conditions, and this was done to allow visualization of exploratory hole and survey planning against the ground conditions as an input to cost-risk analysis. So, as mentioned, the substructure type and the anchor concept has a significant impact on the ground investigation planning for floating wind, but also the point in the project program at which these are defined has an impact as well. So if the project is able to define early on that, say, a tension link platform approach is going to be used, then there's an opportunity to take a more path-specific approach early on and understand ground conditions at each cluster location in a similar manner to floating offshore wind, so with the borehole positioned in the centre of the anchor cluster and targeted to your 3D geophysical survey. On the other hand, we're seeing floating wind farm projects that may be carrying multiple substructure concepts through to feasible detailed design. And in those instances, the ground investigation would need to be agnostic of the anchor concept and the substructure concept. So we're looking more at the approach on the flow diagram there, option 3, where we undertake an approach that captures all these concepts, which gives them potentially necessitate more extensive survey early on to be able to accommodate that optionality later on in the program. So based on the experience of the ongoing projects at the moment, we've noted following aspects of optionality that have informed this study. So potential for changes in mooring radius, anchoring and anchor location at feasible detailed design stage, multiple substructure concepts being carried through, for instance, feed stage, which results in more optionality. Use of an EPCI approach, which means that there's more requirement for the project to provide early GI information, to provide reliable information, and of course multiple anchor concepts being considered at late stages, which results in the GI needing to capture all of these anchoring approaches. So what are the solutions to that optionality with respect to the work done on MA17? Just to see that strategy is dependent both on program and decision gates, as well as ground conditions and ground risk. Potentially seeing a lot of variation in mooring radius across these planned floating wind projects. So for typically for the current UK continental shelf floating wind farm projects that are planned, we're looking at radii between 650 meters and 950 meters for the water depth we're expecting. And the mooring radius is defined later on, so we need a solution that enables us to plan GI and plan and design anchors that is able to deal with this uncertainty in location. The overall approach will be dictated by the variability of the ground conditions and also the anchor sensitivity to this uncertainty when we're considering a ground-based approach rather than an anchor-specific one. And an underlying assumption of this project is that some level of physical data of each anchor location, be this geophysical or geotechnical, will be required to form more sensitive anchor concepts to enable design to proceed. So one potential solution that project looked at is the efficiency of undertaking site-wide 3D UHRS or EAGE, to use the latest terminology, to allow self-profile definition of each anchor location while retaining optionality and maintaining a design program. However, acquiring this data on a site-wide basis early on in the project may necessitate significant pre-FID spend. In terms of how the project programs that we've looked at have been risk assessed, GI overall needs to be proportionate to the level of geotechnical risk at the site to provide value for money and accommodate the project program. So this needs to be a balance between obtaining characterization in each geological unit when we're looking at a ground model-based approach, ability of the ground model to provide sufficient information to enable design, sensitivity of the anchor and cable design to that variability, and if we're able to satisfy these criteria while achieving an acceptable level of geotechnical risk management, then we can consider the site-wide GI approach. So the overall high-level risk assessment approach on the project, a specific geotechnical risk register approach was developed in the project to enable this. This then defined ground variability in the context of those 5 sites. It defined industry experience in those ground conditions, confidence level associated with the data that was collected, and sensitivity level of the concept of the anchor concept that was being considered for each site. This was then fed into a risk matrix, and the SI approach was rated based on that. So higher risk sites, those where anchor-specific GI may be more appropriate, and low risk was where site-wide GI, ground-based GI approaches may be more appropriate. I'd like to just also give a bit of a shout out to this paper from ISPOL 2025, which, while being developed separately from this project, follows a very similar approach. So it's well worth a read. So this risk assessment approach is the one used for the MA17 project that was adopted. So you can see this is broken down into sensitivity class, variability class, and uncertainty level. And this then tripartite risk assessment approach forms the basis of that adopted on the project. As I say, this looks at general approach and AFC sensitivity of the foundation concept and then the uncertainty level at each stage requiring the data. So that will then change as the project moves through into detailed GI phases. So each of the techniques was analysed using Maritime's Optim software to look at program across a variety of start months and to analyse weather downtime estimates. And then comparative assessments were made between different techniques to look at efficiency of using one technique over another, as well as putting these into the context of a project program. One particular technique that was looked at, or problem that was assessed, was the need to understand seabed obstructions across the site to look at the need for free clearance prior to cable burial. Feedback we obtained on this was that objects as small as any size of boulder, so down to 0.2 meters, may represent obstructions to mechanical trenching depending on the morphology, and that it was need to have there was a need to have optionality in cable route and data sufficient to plan cable routes with this in mind. This necessitates quite detailed coverage, essentially early on in the project. So we looked at efficiency of using industry standard techniques such as side-scan sonar to characterize this, as well as synthetic aperture sonar, another more novel or emerging techniques. So this shows a comparison between side-scan sonar and synthetic aperture sonar for a given year, and this shows a normalized duration for the survey. So what you can see is that side-scan sonar is required at much wider line spacing for the same resolution. So we can compared based on the ability to detect a 0.2 meter diameter obstruction. So this means a 600 kilohertz or 900 kilohertz side-scan sonar run a fine line spacing, so 50 meters or less primary line spacing, versus side-scan sonar, that's synthetic aperture sonar, which can be run at potentially much wider line spacing, so 100 to 200 meter line spacing across the site. So what you can see from that plot is that the sail line spacing heavily influences that duration, as you'd expect, and therefore the weather downtime as well. So you can see that while side-scan sonar to obtain that site-wide coverage early on results in significant durations in the winter months, as you'd expect. The limiting line spacing there by using that more emergent technique results in significantly shorter durations. However, an aspect of this is that the use of synthetic aperture sonar results in much larger data volumes, and potentially the overall processing experience and software readiness level for that technique needs to be further developed in the industry outside of a small number of specialist contractors. As you can see, this also has a commensurate impact on cost. So both techniques there we assumed for the purpose of the project were deployed from a standard workboat, so the cost of scales linearly with the duration there. We also analysed the use of AUV versus vessel-based techniques, but this is the focus is on work just for this presentation. As I say, that kind of fairly ground model-based approach, the use of site-wide 3D survey is potentially significant benefit to enabling that approach in terms of understanding ground variability across anchor clusters. That's the sort of turbine scale. However, the industry standard 2D approaches introduce potential uncertainty between the lines through the mathematical interpretation required, which may limit the utility of this for the ground model-based approach to the design and installation, unless your anchor concept is particularly insensitive to variability. The full site approach provides resilience to layout change. It provides the opportunity to decouple GI program from the definition of anchoring layout, and potentially to then take a ground model-based approach to design, which is decoupled from the site scaling program. However, clearly there's a need to look at cost and efficiency of this technique. In the offshore industry to date, it's limited deployment of this technique at this particular scale, site-wide scale. What the comparison that was undertaken for the ME17 project was looking at essentially comparison of 3 different subsurface techniques. So 2D single channel and one channel seismic, which is industry standard, and then what we term as standard 3D UHS approach using audio HRS, using 2D survey vessels or assets. So you can see on the left there, this uses a small number of streamers and sources, and is deployed from a standard 2D survey workboat, potentially need to be deployed at the final line spacing to enable that full site coverage. And then on the right hand side there, we have an oil and gas seismic standard vessel, which we've termed advanced 3D for the purpose of this study. This uses a dedicated 3D survey asset, larger spreads, larger streamers, but this then requires larger vessels, higher day rates, but this enables the survey to run up in wider line spacings, essentially. So we've undertaken an option analysis looking at this approach, the comparison between these 3 approaches, and this used line spacings that were appropriate to each technique. So for the 2D, we looked at a typical approach, characterizing with either 150 meters or 75 meters spaced primary lines across this 1 gigawatt site. We've looked at 30 meter spacing for industry standard 3D UHRS, and also looked at comparing with oil and gas 3D approaches. What we can see here is that depending on the start month, by using the more advanced dedicated 3D UHRS, start to bring durations for site-wide coverage in line with that for 2D, depending on the start month. Of course, so you see that they vary significantly in winter months, but in the summer that the cost starts to come into line with the standard 2D approach. The more more industry standard 3D associated with quite long durations for site-wide coverage, but this is likely more appropriate for dedicated survey and anchor locations if the project is taking that approach. The larger dedicated 3D vessel, despite potentially having increased capex, is based on the use of line spacing and the use of deeper towed sources, has the potential to reduce the program and costs in terms of the site-wide coverage. However, on the flip side, this potentially has more limited assets in terms of acquisition, more limited vessel availability, and the availability using the standard 2D and 3D vessel assets in the industry is likely to be greater, as well as industry experience with those techniques. Briefly touch on geotechnical investigations as well. So similar comparison was conducted for geotechnical investigation. It's looked at in situ testing techniques such as frame CPT, pairing with API drilling and subsea drilling for completion GI and reconnaissance. We're going to focus on the completion GI specific approach for this comparison. So for sites where seabed frame CPTs were feasible, we found as a characterization approach, there was actually a very limited delta in costs between the use of the ground model based approach and the specific approach when you're looking at purely on costs. There was, taking into account there was a very limited cost delta between the two. However, the program may dictate one or the other. So clearly, the program needs to accommodate specific CPT investigation, and that might have to occur at very late stage of the project. So the ground model based approach still gives potentially more program flexibility. Clearly, the cost and program implications of undertaking specific GI at 200 plus individual locations using API drilling, industry-standard API drilling, is significant, and this is limited to potentially around 20 in-region survey assets. So that is also a sort of supply chain constraint potentially that needs to be considered with respect to GI planning, use of the ground model based approach. So briefly sum up. So in terms of the challenges of floating offshore wind farm site investigation, so talked about positional uncertainty and optionality on the anchor and cable layout to the late project stages, greater numbers of individual anchor locations or substructure locations relative to fixed wind, potentially greater variability in ground conditions across substructure footprint. Particular findings that key to a successful approach we found is that enabling optionality is key. So the project is likely to be sustaining significant optionality in substructure type, anchor location, cable routing until quite late stage, and there's a benefit to GI being planned to enable this optionality rather than to try and work around it. Potentially, there's approaches using larger vessels with deep sources and parallel acquisition with AAV to bring durations in line with traditional 2D survey for ground model approaches using 3D data, and enabling optionality, preventing late stage reacquisition of data if there's changes in the layout, while maintaining design program may require additional pre-FID spend. So that's a consideration for specific projects. GI strategy clearly is complex and dependent on inherent geological variability in each site, as well as the project program, the risk appetite, and the substructure and anchor selection. However, we find that ground model-based approaches are, depending on the specific risk appetite, considered appropriate at any of the example floating work sites where there was previous industry experience. As I demonstrated with the CPT-driven approach, maintaining project program may be a greater driver than the DevX cost when considering moving away from the specific GI approaches. We found the program benefits to be a significant driving factor. And emerging techniques such as 3D OHRS, EAGE, and synthetic aperture sonar provide resilience layout change and the opportunity to decouple the GI program from good definition, cable layout, and other project milestones. So as an output from the work, the project also developed an outline workflow to guide the development of project-specific SI strategies, not intended to replace project-specific strategy, but to augment it and provide guidance. The strategy considers the various influencing factors that I've discussed in the presentation, and acts as a guide as to where it might be appropriate to select one board strategy over another. In terms of next steps for the MA17 project, this will be aspects of this project will be released as a public summary report over, and that'll be sort of announced by Catapult in due course. So closing thoughts and developing best practice, how could what will need to be done to build on this work? So identification and mitigation of the sensitivity of the anchor concept to the uncertainty is likely to be critical in the application of a ground model-based approach. And it's recommended to develop a site-specific approach to geotechnical risk management relative to the sensitivity and defining bounds of acceptable uncertainty. That's a key recommendation. How would we go about doing this? I think this is an aspect that needs more attention by the industry and further assessment. Essentially, you can look at the use of reliability-based design to understand what the uncertainty, the bounds of uncertainty could be, how sensitive the anchor is to uncertainty. And this may be more relevant for anchor types which are precise. A brief flash up the useful paper on the observational method. This is a technique which is seen significant body of use in onshore construction, but perhaps more limited use in offshore site investigation and installation. This may be relevant to anchor types where it's possible to proactively implement mitigation measures, so to observe the ground during installation and then act accordingly to put in place mitigation measures if the ground conditions are different to what is expected. This likely won't apply to all anchor concepts. And finally, potentially further approaches to consider using the ground model approach to accelerate design and installation planning, but then to confirm ground conditions in a further stage prior to installation. So you could look at that as a kind of hybrid with the observational method. Finally, I'd like to acknowledge my team members at Maritime who form part of the team for the MA17 project, by thanking the area Catapult team, as well as the Floating Offshore Wind Centre of Excellence project partners shown on the right there, and also industry stakeholders and contractors who supported and provided information to support the study. So thank you very much, and I'll open the floor to questions. Thanks.
Thanks, Jordan. That was a brilliant talk. It was really comprehensive. I can't believe you packed that much information into that amount of time. And I really loved the field photos squeezed in as well from the QRA field trip of the soils in the wild. So really, really great summary. Thank you very much. I think we've got a few minutes, so maybe 1 or 2 questions. If anybody wants to ask something in person, put your hand up, or I can read some questions out from the chat. We can start with Dixon's asked a question. He says, great plot for site data versus risk and uncertainty. Would the plot benefit from adding the current standards and recommendations for GI so quantities are included?
Yeah, I think that plot referring to the risk against leaks. So that's actually from the OC guidance. So that's the general sort of concept in terms of doing sufficient GI to characterise an acceptable level of risk, but not necessarily kind of undertaking more GI is necessary to characterise that risk. So I think there is a case for kind of adding specific milestones for floating wind to that, adding specific project considerations. That's what we've tried to do with. There is a workflow in the Catapult report which sort of attempts to look at that.
Perfect. Jack asks, with the relatively shallow depth of interest, is a UHRS EHRS survey required? Could you not achieve similar results with SBP? With the SBP being deployed from less specialist / cheaper vessels and better scalability, as it is simpler equipment?
Yeah, that's a really good question. Our experience with SPP is that, well, firstly, in terms of anchor embedment depth, typically for piles, suction caisson, suction anchor type concepts, you're looking at maybe an influence depth of between 20 and 40 meters, depending on the specific concept that's required. In ground conditions such as mix of tills, stiffer, denser materials, the sub-bottom profile penetration may be more variable. So we assessed 3D address to be a more appropriate technique for guaranteeing that depth of interest in terms of the quality of the data and the depth of penetration. We did look at 3 sub-bottom profile approaches as well, but these have to be run at a very fine, almost sub 10 meter line spacing. And again, we felt these are more appropriate for maybe targeted characterization around anchor locations at late stage rather than site-wide characterization.
Maria Paula, do we have time for more questions, or should we wrap up? Silence. I'll ask one more then. Vicky's asked, how does this time saving in acquisition translate into processing time?
That's a very good question. The processing time for 3D is significantly longer than 2D, more expensive, so that needs to be factored in. But what we're seeing is that there can be multiple stages of delivery, so essentially there's fast track approaches that can be used for initial characterization that are available quite quickly after demob, and then for maybe more detailed characterization, design applications, even if you're looking at the ground-based approach, full track process volume that's available later on would be more appropriate. So I think it just needs to be kind of deliverables need to be fitted to specific task and application really.
Thanks, Jordan. Well, I think we'll probably have to wrap it up there, if that's okay. So it's getting quite late in some locations, but maybe we could ask you, Jordan, to answer some of these questions on the our LinkedIn page, and people get back to the answers there from you. That's okay with you?
Yeah, that sounds good.
Fabulous. And yeah, just as a reminder, if anybody has any ideas or wants to present their work or anything any topics they're interested in, please let us know at our LinkedIn page or email any one of us. And yeah, once again, thank you so much, Jordan, for putting yourself forward for this first webinar. It was absolutely brilliant. Thanks for sharing with us. I hope everybody else has a lovely evening. Thanks, everybody.
Yes, bye.